Start recording again. Okay, this chapter is very exciting to me because this is where we're going to start thinking about how our charge is moving around. Okay, and this chapter is going to be called current and resistance. And current, when we say current, we don't mean, well, you can kind of picture it as, water current, but we're actually trying to figure out how are electrons moving around inside our conductors. Okay, but before we start, otherwise I'll forget about this guy again. Just another scientist's birthday, right? This is actually March 3rd, which is last Friday, so we're a little late. But hopefully a lot of you guys know who this guy is, Alexander Graham Bell. What did he invent? Telephone, yeah. So he got credit for inventing the first telephone, let's just say that. Okay, he was actually the first to be able to patent one that was practical, meaning he's actually able to, just pick up a phone from the east side of New York and then call someone on the west side of New York just by connecting a wire between the two. Okay, and of course he's also, founder of the American Telephone and Telegraph Company. What does that acronym stand for? It's just AT&T, yeah. So that company is still around, right? So it's kind of cool. Anyway, so, and he does this because he understood current and resistance, right? So let's talk about how does current and resistance affect our everyday life, right? So whenever you turn on a light bulb, even you turn on fluorescent bulbs, right? Whenever you plug in your computer, whenever you control your muscles, that also is affected by current. And that's because everything we do, like 99% of our daily lives, is controlled by electricity and magnetism. Okay? And we're going to try to figure out how we can control the motion of these electric charges in this chapter, or at least how to quantify it so we can actually identify how fast things are moving around. So let's zoom into our little piece of metal, right? Imagine this little metal cup, right? I'm going to zoom in so we can even see the individual atoms on this little metal cup. Okay, if you see the little individual atoms, right, you'll see that there's going to be a bunch of positive charges where the nucleus are located, right? And then there's going to be like a bunch of electrons just kind of whizzing around. Okay, these electrons are negatively charged. Right, I'm going to put a little minus sign everywhere here, right? But they're just kind of whizzing around with some velocity v. Okay. The ones that are not bound to a particular positive charge, okay, meaning metal has this property where there's just going to be excess electrons just kind of floating around. Okay, it's kind of like just an extra extra charge around. Okay, these are known as conduction electrons. Okay, meaning there are electrons that conduct electricity. Okay, hopefully that makes sense. Also known as charge carriers. So you're going to hear me say one and the other. You can use both. They're just synonyms of each other. Okay. But the main thing to understand is that either conduction electrons or charge carriers, they are things that are moving the charges around. They are the thing that actually move charge from one side to the other. Right? They are the ones that move from the battery onto the positive plate of your capacitor. Right? You have a little battery here. Right? The charge carriers are the ones that move up to here to make a positive charge, and then the negative charge goes over here. They are the ones that moves around. Okay? And these are easy to move around when you have a conductor, but still, right, if you look at this picture up here, right, these little electrons, right, they're kind of like bouncing around this positive nuclei, right? They don't get to go on a straight path, right, if they're traveling through a little wire. Okay, so let's say I start off with an electron here, right? It kind of bounces here, bounces here, bounces here, bounces here, bounces here. It doesn't go in a straight path across, right? Oops, I'm trying to draw a path up, right? Okay. Okay. The speed which these electrons move across a conductor is known as a drift velocity. Drift velocity. Okay. Okay. The reason it's called drift velocity is that if you imagine instead of electrons, right? Imagine like a little leaf in the river, right? When a leaf in the river is kind of following a current, right? It can bump into little reeds and rocks in the river, so it doesn't actually get to travel in a straight line. It's just kind of bumping around. Okay. Another way to think about this. So when I was a kid, they had these in the fairs, where you put a little. It's actually not a ball, but a little circle, where it just kind of bounces up and down, bounces up and down, bounces up and down. And if it happens to land in the right place, you get a prize or something like that. Anyone ever seen that? Is that really old for me? Okay, but to imagine that it's the same thing with electrons, where, right, instead of being able to go straight down straight down the hill, right, it kind of runs into this little peg, bounces up, runs into this little peg, bounces up, runs into this peg, bounces up, bounces up, bounces. So it takes, maybe like a minute for the little peg to the little circle to actually get to the ground, right? Okay, so it doesn't get to go in a straight line, so it drifts down the hill, okay? Okay? And typically, the value for drift velocity is 10 to the minus 4 meters per second, okay? That means that if I take a wire, I have a wire around, right? Looks like just this little USB wire, right? Right? You get a longer wire. Okay, I'm gonna disconnect this real quick. Okay, right? So that means, right? Right, let's say I have a wire that's 1 meter long. For the electrons to get from this side to this side, if it's 1 meter, it'll take 10,000 seconds. How long is 10,000 seconds in like minutes? You guys want to estimate what that is? Right? 10,000 seconds. Convert that to minutes. It's 60 seconds per minute. Right? How many minutes is that? Anyone have an estimate? I'm sorry? A lot, right? 10,000 divided by 60. Okay. That is 167 minutes, or about like 2.3 hours, right? So once again, right, pick up that wire again, right? I don't want to disconnect the monitor again, right? Imagine you have a wire, right? Does it make sense for the electrons to take like 2.5 hours to get from one side of your charging port, your charging, your power brick, to your laptop? It doesn't make sense, right? So we're going to try to figure out how does electricity actually gets moved on a conductor, okay, if the drift velocity is so slow, okay? And this idea of drift velocity, once again, right, is how fast are the electrons moving across that wire, right? Right? But it doesn't get to go in a straight line, so it's going to go up and down, up and down, up and down, so it's actually kind of drifting down the little river very slowly, right? Okay? What we're going to do is we're going to try to quantify this. We're going to declare something called an electron current, okay? When I say electron current, it just means, okay, how many electrons are moving across that little section per time, right? It's kind of like speed, right, that way, okay? Number of electrons per time, okay? How many electrons are going into this little, tube of conductor per unit time, okay? So this will have units of number of electrons per second, right? Okay. Okay. So what we're going to do is do something else, that one more variable we have to declare, right? We're going to call this thing let's not call it this way, okay? A lowercase n is going to be the number of electrons per volume, okay? This is known as the electron density, okay? And the reason we need this electron density is because different material has different electron density, okay? So for example, copper has an electron density of 8.5 times 10 to the 8 electrons per cubic meter, okay? This is the number of electrons per meters cubed. So if you've got a big giant block of copper, right, that's going to weigh a lot, right, you're going to have 10 to the 28 electrons inside that copper. That is the conduction electrons, okay? Those are the ones that are free to move around, okay? They're not bound to each of the individual nucleus, okay? Gold is a little bit less. Aluminum is even less, right? So these are numbers on the order of 10 to the 28. There's a lot of electrons around, right? Okay. So note that when these electrons are moving through your, let's say, some copper wire that's cylindrical shape, right? Right? It has some drift velocity Vd, right? And let's say after some amount of time, it goes through a delta X section of the wire. So the electrons move from this, the electrons move from here, after some time, in general, it moves to this position, right? After it's bouncing around in there for a while through the drift velocity, okay? So therefore, what we can do is solve this equation up here, which is the reason why the book did it this way, right? The number of electron is actually the same thing as the electron density times the volume, right? Those electrons are passing through, okay? So we can start off down here, right? Number of electrons is the electron density times the volume. So this V is not the voltage, it's the volume, okay? So unfortunately, it's the same letter, okay? And from the geometry here, right, the volume of this, right, is just the area of this little disk times the distance that the electron has moved, right? So therefore, right, you can box this. You can see that, right? The area, the cross-section area times the distance that the electron moved is the volume. Question?
I didn't catch it. What's the difference between the capital and lowercase n?
Capital N is the number of electrons. Lowercase n is the electron density. Okay? How many electrons you have per volume. Okay? So unfortunately, there's a lot of letters around. Okay? Right? So volume, okay? Sorry. So break this up into delta x here. Right? This delta x here is interesting. Remember that distance is just the rate times the time, right? Distance equals rate times time. Therefore, delta x is actually the drift velocity times delta t. Okay, hopefully we'll get to the end here soon. Well, at least get to the end, get to this equation soon. Okay, so now going back to our definition of electron current, right? We're interested in how many electrons are moving through our copper wire per time, right? The number of electrons we just find out is up here, so I can copy that over. The electron density, area, drift velocity times delta t, and then all of that gets divided by delta t. And the whole point is that so we can cancel out the delta t, right? So therefore, the electron current passing through the conductor, right, is actually the electron density times the area times the drift velocity, okay? All right, so I think tomorrow I'll start off with this equation, do an example, and then get started from there. I think that's a good stopping point.